So let's talk about the image of a group morphism. So we'll define the image, just like I guess we would define the image of any function. So let's phi from G to H, a group morphism. And then so the image of phi is, I guess I should say G and H are groups. Image of phi is set X in H such that X is equal to phi of G for some G in G. Right? It's all of the things in H. It's all of the things in H that can possibly can possibly be hit by something being mapped via phi. Right? So if I start with everything in here and I apply phi, everything that it hits, that's the image. And so now here's our little theorem. Maybe it's a lemma, maybe it's a theorem. Our theorem is that image of phi is a subgroup of H. So there's going to be, let's see here. There's going to be, so how do we prove that something is a subgroup? Well, we need to prove three things. Well, I guess first of all we need to prove that this is a group, and then we need to know that it's a subset. This, well, we already know it's a subset, so that'll tell us that we can use the the multiplication from H, and in particular it'll be associative. That's fine. So we don't need to worry about associativity, but what we really need to prove when we're proving something's a subgroup is we need to prove the identity axiom, we need to prove inverses, and we need to prove closure. And this is something to watch out for. People forget to prove closure sometimes, but you really do need to. So let's prove all of these. So first, let's start with the identity axiom. So what we need to do is we need to show that 1 is in the image of phi. And so that would be the same thing as saying that there exists a G such that phi of G equals 1. And it turns out there is such a G. In fact, so take G equals 1 by the properties of group homomorphisms. Phi of 1 equals 1, so we're good. So now for the inverses axiom, we'll do something similar. We need to say given A in image of phi, need to show that A inverse is in the image of phi. And we can do this. We expand the definitions, right? We know that A equals phi of G for some G, and then we consider phi of so A inverse equals phi of G inverse, which again by the properties of homomorphisms is phi of G inverse. So we can take G inverse. And we're good. Finally, let's prove closure right here. And so how do we show that something is closed? We need to show that if A and B are in image of phi, then AB is in the image of phi. So again, we can just expand the definitions. So A equals phi of G, B equals phi of G prime. But then, of course, the defining property of a homomorphism, phi of G times phi of G prime, which is equal to A times B, this is actually equal to, well, it'll be equal to phi of G times G prime. So we can take G times G prime, and that will, by taking G times G prime, that will satisfy us for the closure axiom.